All right, so let me first thank Shubham and all the organizers for holding this event and asking me to talk about invention of transistor. It's both a easy as well as a difficult topic. Easy because I think all of you know about transistors, so I don't have to exert myself to explain perhaps much of it. And most of you would know something about the history of the transistor. It's difficult because I've been given an hour and I have to make it worthwhile that you don't get bored listening to whatever I have to say for an hour. Okay, so that's a difficult part of it. Anyway, so let's start. The first thing is, we all know, as Shubham said, electronics has impacted almost all aspects of our life. And if we go back and would like to trace where, for example, electronics started, then this is one of the events. Today we are celebrating the invention of the transistor, but electronics had almost like 40-year history before the invention of the transistor. And 1906 was the invention of this particular device, triode, by this person here, Lee D. Forrest here. And this really launched electronics. And the main characteristics of this particular device was that if you look at this particular device, it's a three-terminal device. There's an anode, there's a cathode, and there's a grid. And so there's a current which flows between anode and cathode, and this current could be controlled by applying a voltage to the grid. And so it had a property which we need to remember of transconductors, that the current flowing between one pair of terminals could be controlled by voltage applied across a separate pair of terminals. Not only that, you could perhaps see this property in many devices. The transconductors was much larger than the output conductors, which means that the current was far more sensitive to the grid voltage than to the voltage applied to the same pair of terminals. And that is what was very surprising or very interesting about this particular device here. Normally, one would expect current flowing between a pair of terminals to be sensitive to voltage applied across the same pair of terminals and less sensitive to something applied remotely, while this was just the opposite. And if you just rearrange this equation, you can easily see that a small change in grid voltage would result in large change in the anode voltage, and that resulted in amplification. This was the first patent that was filed. This was in 1907, January of 1907. And the tube had been invented a little earlier than that. That's why I've written the date, 1906. All right. As Shubham mentioned, that a single transistor, let's say a triode, can do some interesting things. But if you really want to do something substantial, you have to connect several of these tubes together. Just like a single neuron by itself is interesting, but it's only when you have billions of neurons talking to each other, then you get intelligence and you get all sorts of interesting things. So similarly, if you want to do interesting things with a device like, let's say, a triode, you have to connect lots of them. And this is an example of an early computer. 1946 is an early computer, and the ENIAC. And if you read about it, you can see here that it's not a very complicated computer. Has about 17,000 active elements here. And the trouble with it is, it occupies an entire room, weighs 30 tons, and consumes kilowatts of power, hundreds of kilowatts of power. And not only that, the whole thing was very unreliable. And every day, some of the vacuum tubes would fail and they had to be replaced. Right? So the main problem with this particular device, although revolutionary in nature, was that scale of integration was limited. And this is an important point because if you want to do, as I said, something interesting, you have to connect lots of them in order to realize that particular functionality. And integrating lots of it created this kind of a trouble here. Well, this is my description of some of the landmark events in the history of electronics here. So I've written here 1906, invention of triode. We had 40 years of we had 40 years of vacuum tube based electronics here. And today we are talking about a break in this particular evolution, which is the invention of the transistor, 1947. before I describe how this particular transistor was invented, I just wanted to point out, I've told you a few things that were problematic with respect to the vacuum tubes. This is in the words of William Brattain, one of the inventors of the transistor. After having invented the transistor, this is what he's writing. What are the advantages of the transistor, okay, with respect to this? So let me highlight. It operates without any warm-up time. At the top of the list is without any warm-up time, because prior to that, everything was mostly made out of vacuum tubes. And vacuum tubes had a filament, you had to heat it up, and then the cathode would emit the electrons and anode would collect it and all that. So if you had a radio and if you switched it on, you had to wait for the warm-up time. Things had to warm up and then only would start working. So at the top of his list is it operates without any warm-up time, okay? Then it uses merely a fraction of power, very low power here. Extremely reliable. And he says here, trouble-free for decades. You could have these devices running without any problem for decades. High frequency, high speed operation. And at that time, he was writing that it can be made smaller than a pinhead, and which represents extreme miniaturization, right? So these are some of the reasons why that he lists why transistor was a revolutionary device. And this was a device that they had invented. A schematic of the device that they invented. This is a block of germanium. This is a block of germanium. There are two contacts to it. And if you apply voltage across one pair of terminals, an amplified version would appear across the load here. Now, this is what we are going to discuss. How did they develop this concept of the transistor? What is the genesis of it, okay? So the trouble with going back and identifying or talking about history of anything is, how far back do you go? Just like for every why that you ask, you can always ask another why, and there's an endless series of whys that you can ask. Similarly, if you want to understand a particular invention, a particular discovery or an invention, you have to go back and look at the history, what led to it. Now, if you talk about those events prior to the invention of the transistor, then you may ask what led to them, those particular incidents, right? And then you can go back and back and back, and there's no end to it. So we have 1 hour today to discuss the conception of the transistor. And my starting point is, the first one is the first description of the transistor by this person called Julius Lilienfeld. So as I said, people were aware of the problems with the vacuum tube, and they were looking for alternatives. And this person, Lilienfeld, he filed a patent in 1925, and he described the device, basically a conductor, which I'll just show you. This was his device, a piece of glass on which there were 2 electrodes. This is glass here, 2 electrodes, copper here, 2 electrodes, copper here and copper here. And on top of that, there was a film of a semiconductor, right? And embedded here in this part was a piece of aluminum here, right? So he never made this device. He's only describing that if you have a device like this and current flowing between this electrode and this electrode here, between a pair of electrodes, could be controlled by voltage applied across this pair of terminals. Remember, at the back of your mind, you have to keep the triode in your mind. Current flowing between cathode and anode could be controlled by a grid, voltage applied to a grid. So that's what he's saying. Current flowing between these 2 electrodes could be controlled by an element, an electrode embedded here in glass, and that you could thereby achieve something like a triode kind of a thing here. So it was an interesting concept. This concept is what one would normally call as a field effect principle, that using an electrostatic field, you alter the charge density in the material that is over here, and thereby you alter the current flowing between the pair of electrodes here. So that's the field effect principle. And based on this principle, eventually a transistor was invented, which is called the thin film transistor. That transistor forms the backbone of all the laptops and cell phones and all that you carry. In each one of them, there are millions of such TFTs here. But this did not play a big role in the invention of the transistor that we are talking about. This concept, this patent was filed, but nobody could really fabricate this particular device here. And I would say it was sort of lost in history here. If you really want to trace what led to the birth of the transistor that we are talking about, I think you have to go back and talk about what are called point contact diodes. Point contact diodes, example here shows, this was a very popular material earlier called galena lead sulfide. And there are two contacts to it. One is a very large contact here, so it almost forms like an ohmic contact. The other one is a point contact here, right? And that's where it is called, it's like a very thin wire, which is pressed on top of the crystal, which is there here, right? It's also called crystal diode, is also called cat's whisker, because this wire that was there, it was like a cat's whisker. So it was also called a cat's whisker diode here. So point contact diodes had been discovered by this person here called Ferdinand Braun. Ferdinand Braun, and this was in 1874. He had discovered that when you make these contacts, you get rectification. That significant current flows in one direction and less current flows in the other direction. So he had discovered rectification in this particular crystal here, and in other materials as well. But they didn't know what to do with it. I mean, fine, it rectifies, but what do you do with rectification at that particular point of time, 1874, right? The next important event that I would say, a very important event that occurred, was this patent that was filed by Jagdish Chandra Bose here, J.C. Bose, in 1901. If you go back and see in 1901, so what happened at the time was radio waves had been discovered. There was a person by the name Hertz who had demonstrated radio transmission. And Jagdish Chandra Bose was a student in England, and he had seen the demonstration of radio waves. He came back to India, and he started experiments on radio waves, various aspects of radio waves. And in the course of his experiments, he invented, note that I've not written here crystal diode. It was a crystal diode, but he was the first one to show that this diode could be used for rectification, for detecting radio waves. And you know, very simple radio receivers could be built, that you have a resonance circuit, yeah, and then you have a diode which acts as an envelope kind of a detection, and then you have an earphone, right? So this was the simplest radio receiver that could be built using the crystal detectors that you see here. And so he was the one who now showed that, look, with the rectifiers that Ferdinand Braun had discovered and invented, you could do something interesting, and it was very important for receiving radio waves, these crystal detectors that are there. And once he did that, once he filed his patent, a lot of other people started working on it, okay? And amongst them is this person. So this is the patent for Jagdish Chandra Bose. Among them was this person here, Picard, who is credited with having first used silicon as a material on which he could get very good rectification properties and could use it for a radio detector here, right? So note that as early as 1906 here, silicon was known as a good material with which you could make crystal diodes, and you could use it for detection here. Let me now switch to, so what happened was these diodes were, people knew that you could use them for detection of radio waves. And for a while, these were used. But then, as I already look at this date here, 1906, right? That's the time when these crystal diodes for radio detection are being used. But at the same time, as I said, triode had been invented, vacuum tubes were developing fast. And those tubes, vacuum tubes and all that, they had their problems, but they were far more reliable compared to these detectors that you see here. For example, if you take a silicon detector and you make a point contact diode, it was highly unreliable. You know, you would go and put your wire at one place, it would not work. Then you move it around at some other place, it would start working. The rectification would be in one direction at one place, the rectification would be in another direction at a different place. The reason was that semiconductors had lots of impurities, N-type, P-type. We know in hindsight, N-type, P-type. So the nature of the diodes changed depending on where you probe, right? So they had lots of these problems. Vacuum tube didn't have those. They had reproducible characteristics. And so almost the entire electronics, entire interest shifted to, even in terms of radio waves, it shifted to vacuum tubes. And these crystal detectors, they were sort of forgotten. All right, so even though they had been invented, they had interesting properties, but they were forgotten. until you come to World War II. And when you come to World War II, and that's where most of the story would revolve around what happened at Bell Laboratories. And during World War II, interest in crystal detectors revived. And the reason was that radar became very important. And radar, they were looking at very high frequencies, like in gigahertz, and vacuum tubes are not doing very well. Rectifying a signal at gigahertz frequencies was becoming very difficult with vacuum tubes. And I'll come to one of the key persons who suggested that why not use crystal detectors again, that they would be much faster than the vacuum tubes, okay? But before that, most of the action, at least as far as the discovery of the transistor is concerned, took place at Bell Laboratories. And I'll talk a little bit about the people who were involved. Mervyn Kelly was the director of research at that particular labs during those particular period. He later became the president of Bell Labs also. And he put together a group for research in solid state devices, which can eventually act as replacement for all the switches that were there, electromechanical switches that were there in telephone systems. Brattain, who's one of the key persons in the invention of the transistor, he had already been there at Bell Laboratories very early on, 1929. And he had been working on vacuum tubes and crystal detectors for a long time. 1936, Shockley finished his PhD at MIT and joined Bell Labs. And he also started working on various aspects of these detectors here. So these people were there at around 1936. Yeah. So as I said, wartime, because of the interest in the radar and detecting these very high frequency signals here, this person, George Southworth, also at Bell Labs, so he was looking for a replacement for vacuum tubes. Vacuum tubes, as I said, were not working very well. And he went around, he went to some old shop and he asked for some crystal detectors, whether they had some old crystal detectors. As I said, they had all gone out of use by the time. And so he found a crystal detector, silicon crystal detector. He brought it to his lab and then he tried to detect the microwave radios using that particular crystal detector and worked very well, right? So he had found something which was much better than vacuum tubes. Note that vacuum tubes had already reached a fair level of maturity and they were not doing very well here. So George Southworth discovers that these detectors can be very useful for in the microwave radiation, for detecting in high frequency radio waves here. And so he goes and he talks to his friend here, which is Russell Hall. He goes and talks to his friend who was, working with an experimentalist working with detectors and who had some prior experience. So he told him, look, this silicon detector has some interesting properties, can be very useful for us. Can you further look into that? And so Russell Hall looked at variety of, interest in crystal detectors was again regenerated, and he looked at a lot of materials and he started looking at which material would give the best characteristics. And during his experimentation with silicon, he's the one who first sort of discovered, you can say, a PN junction. He discovered PN junction, Russell Hall discovered PN junction. Not only that, during his experimentation, there was a light nearby his setup, and when the light would fall on his PN junction, the voltage would be generated, a photo EMF, right? And so he's the one who first discovered the solar cell. That silicon would act as a solar cell. He could, he was seeing a generation of voltage in response to the light that was falling on the semiconductor here. So he played a very important role in identifying a PN junction within silicon and its properties with respect to this. There were two other gentlemen. I'll not talk more about them, Scaff and Thier. These were the metallurgists at Bell Labs. It was very important for the discovery of transistor and many other developments later on that you had pure samples of germanium and silicon and all that. These two gentlemen played a big role in making available very high quality germanium and silicon available for experimentation here. All right, so silicon detectors then, as I said, they attracted interest and a lot of development took place. This is a chart which shows here the development that took place in silicon detectors in terms of the noise performance of the radio detection, radio receiver here. This is where is the vacuum tube here. And, the only point that I want to make is, look, a lot of work took place during the war, during Second World War, and silicon detectors underwent a lot of investigation, and a lot of improvement occurred in terms of their performance. So people knew the silicon and germanium detectors very well towards the end of the war. What was Shockley doing? Well, this is an example of 1939. This is an entry from Shockley's diary. And he's thinking of, the whole group was constituted to look for a replacement of a vacuum tube. And this is one of the entries in his diary dated 1939. So he's thinking of how to come up with a replacement for a triode, right? So he's thinking of that if I take a copper grid, this holes that you see here, so it's a copper grid. And he's thinking that if I take a copper grid, oxidize it, it becomes cuprous oxide. Cuprous oxide is known to be a semiconductor, and people had made detectors on it. So he's thinking if maybe one can get cuprous oxide, make contacts here, and make a contact to the grid. So note that the thinking is in the direction of the triode, that you have a cathode, you have an anode, and you have a sort of a grid, and that's how you could control current. That's how, for example, Shockley is thinking about it in 1939. All right. As I said, the war ended, and in 1946, the work on semiconductors is intensified. So Bell Labs goes back to its original idea of find a replacement for vacuum tubes so that it can be used for electronic switching, right? And these were the people that were there in the group that was at the Bell Labs that was there. Morgan and Shockley, they were the managers of the group. We had Brattain, Pearson, Bardeen, Gibney, Moore, All, Scaff, and Thior, some of the people that have listed here. And so let's read here. At the first meeting of the group, it was decided, this is from Walter Brattain. He's recollecting the invention of the transistor in this particular article in 1968. At the first meeting of the group, it was realized that in spite of all the work done before and during the war, we were still very far from a good understanding of the semiconductors. One reason was that copper oxide and other semiconductors on which early work had been done was very complicated solids. Silicon and germanium were the simplest, and the decision was to try to understand these first, understand silicon and germanium. Our work was directed towards a fundamental understanding of the problem, understand semiconductors as well as possible, although we were well aware of the technical importance of a semiconductor amplifier if they could make it. So at the back of their mind, it is that if you understood semiconductors very well, the whole thing could lead to a semiconductor or a solid state amplifier. So at the direction of Shockley was a part of the group, and he said, well, why not think about, he came up with this particular idea of a field effect principle, that if we are trying to invent an alternative to vacuum tubes, maybe this is the direction that we should proceed with. A field effect principle that I talked about, that Lilienfeld came up in 1920s, right? So Shockley, this is a diagram from Bardeen's Nobel lecture. So Shockley came up with this idea here, is that if you take a semiconductor layer and you apply a voltage across it, the current would flow. And if you're able to place another electrode on top, because of the capacitive action or field effect action here, if you apply a voltage at this particular plate here, you will induce electrons here and thereby modulate the conductivity. And therefore, through this particular voltage, you could alter the current flowing here, right? So that was the idea, that the initial direction was to use this particular structure to realize a solid state alternative to vacuum tubes. So at the instance of Shockley, the whole group started effort to realize this particular structure here. And so this is in terms of band diagrams here. By the time they already understood conduction band, valence band, concept of electrons, holes, all that was understood, right? So they could understand what would happen if you apply a voltage here, and many of you would be familiar how the bands would bend if you apply a voltage, and accumulation of electrons and all that would occur here. The thing was that they did experiments to make a device based on this field effect principle, and all the experiments failed. They did not see modulation of, they were expecting modulation of current as a result of the voltage, and they saw effects which were 100th or 1000th of what they were expecting. Very, very feeble effect. That this voltage that they were applying here was hardly having any effect on the current flowing between these two pairs of terminals here, right? So this was a failure. Not only that, so this field effect principle, theoretically it seemed sound, but it failed, right? And not only that, before that also they had many puzzling questions. For example, if you take a metal and you deposit it on a semiconductor, you would get a barrier, and you expected that it would act like a diode. And you would expect that the characteristics of the diode would depend on the nature of the metal here. But no matter which metal they deposited, they found that the characteristics remained independent. So that was also very puzzling in terms of why the diode characteristics are independent of the metal. So there were many other puzzling characteristics associated with these detectors. Also, the experiment on field effect was the experiment failed and did not yield much control over the current here. And Shockley brought this to the attention of Brattain and said, can you look into it? Brattain was a theoretical physicist and said, can you look into why this is happening? Why is this field effect principle, why is it not working? And Brattain came up with this idea or this hypothesis that at the surface of a semiconductor, there are a lot of surface states. Surface states, which is there in the band gap. There are a lot of these within the band gap. There are a lot of these states here which trap electrons. So his idea was that whenever, when you're trying to create a when you're trying to create a, let's say, a layer of electrons at the surface, what is happening is so what was happening was that when you're trying to apply a voltage here, all the electrons are not going as free electrons, but they're going into the surface state where they're immobile. And that is the reason why this field effect principle was failing. So he came up with this hypothesis, and with this hypothesis, I'll not go into the details. He could explain some of the puzzling aspects of why the nature of the metal didn't affect the characteristics of the crystal detectors earlier here. So this hypothesis of surface states was introduced to explain why this was not happening. So the whole group's attention then shifted to understanding surface states. So they realized that if they were going to invent a transistor, invent a alternative to triodes based on this field effect principle, they had to understand surface states very well and somehow solve the problem of surface states. All right, so the focus then shifted towards understanding surface states in a piece of semiconductor. And Brattain did a number of experiments to understand. And the kind of experiments that he was doing, so he was measuring what is the potential. So the effect of the surface states, if you look back, the fact that there are lots of states at the surface was that these states would capture electrons from the bulk. If you have an N-type semiconductor, they would capture electrons here, and they would create positive charge here, as a result of which you have a barrier. You have a potential barrier here. So what Brattain was trying to do is measure how much of the barrier that is there at the surface, trying to understand. And so, if you want to modulate the barrier, if you want to alter its properties, the first thing that you would like to do is measure the how much of the barrier that is there here. So he was using a setup which I'll explain, which is important to understand. So he was using a setup of the kind that is shown over here. There's a block of, let's say, germanium, and there's a reference electrode. And so let me explain what he was doing. So the idea was that you have a semiconductor, and you have, let's say, an ohmic contact here, and this is a probe, another piece of metal kept fairly close to the semiconductor, right? Note that what is the goal? The goal is to understand what is happening at the surface of the semiconductor, how much of a barrier, potential, and things like that is there at the semiconductor. So if you go back to, those of you who are familiar, if you go back to the energy band diagram, and this is the energy, this is the probe. Let's say the probe is here, a metal. And semiconductor, even though it's shown more like a metal here, it doesn't really matter here. So it has a different work function. And so this is when the two are isolated. The semiconductor and the probe are isolated. Now, if you connect them up with a wire, what would happen is, as many of us know, the electrons would flow from region of higher firm energy to lower firm energy. There's a transfer of electrons, right? And what happens is this gets charged here. There's a negative charge here. There's a positive charge here. And then there's a potential difference that sets up between the two here, right? The difference of potential between the probe and the semiconductor results in creation of this charge, and there's a potential difference here. The issue is, how do you measure, for example, this potential difference? So what you can do is, so this is a contact potential between the probe and the semiconductor. So if you alter the separation between the probe and the semiconductor, if you vibrate the probe, so what would happen is, if you vibrate the probe, the capacitance here will change. So I is dq by dt. The voltage between these two is fixed, which is the contact potential. The separation between them is changing. So basically the capacitance is changing, right? So what you end up is getting is a current flowing in the circuit here. So if you make an arrangement like this and you vibrate the probe, you will get an oscillating current in the wire that is there. So now what you do is you apply a bias at here. And what you try to do is you cancel the voltage that was there inside the contact potential through this here. So to create a flat band condition. If you do that, if you create a flat band condition here, there is no charge here. There is no voltage. The net voltage inside is zero. Effective voltage is zero. And you would get a current equal to zero here in the external circuit. So even though you vibrate this, you won't get any current here. So the voltage that you need to apply in order to cancel the voltage that is there inside is then a measure of how much is the contact potential. So I'm just trying to give you a hint that through means like this, one could study, for example, the contact potential between the probe and the semiconductor. And Brattain did a number of experiments with light also falling in it. And so he could study what is happening at the surface of the semiconductor through means like this here. So in the course of his experiments of this, so what he was doing was trying out, looking at the effects of light, for example, trying out different materials and all that he was trying to figure out. Shockley, who had suggested that why not use this particular structure for creating a alternative to triode. So he said, well, why don't we go to lower temperatures? If we go to lower temperatures, then the surface states will not respond at lower temperatures. And maybe if we alter the voltage here, we will start seeing changes in the bulk. So he was saying, suggesting do experiments at lower temperature to immobilize charges that are there at the surface here. And so Brattain started doing experiments, trying to figure out what is happening at the surface at lower temperature. And so when he was doing at lower temperature, he wanted to investigate what is happening at the surface at lower temperatures. He found that when you go to lower temperatures, water would condense on top. Water would condense, and that would create a problem for him. So what he said was, well, he put some liquid there, a solution here, so that the water, some insulating liquid there, so that the water and others will not condense and interfere with the experiment, right? So the idea was some inert fluid, if I put here, then that would cover the surface and then to study the properties. Now, when he did that, when he put this fluid here, and then he started investigating various kinds of fluids. And he saw that depending on the fluid that you put, you would get different amounts of potential that was there inside the semiconductor. Some fluids gave very high potential here, some gave less and all that. And in the process, he even used some electrolytes, which had some charges inside. Right, so in order to avoid condensation, he started experimenting with various kinds of fluids that were there here, and looking at what influence that they have. And then one of his friends, Gibney, suggested, he said, while you are looking at it, why don't you apply a potential to that fluid? If it's an electrolyte, why not apply the potential to the electrolyte? Right. So what he did was he applied a potential to the electrolyte, and he could see that depending on the potential that he applied to the electrolyte here, the barrier that he was able to measure earlier, the barrier and all those, he found that he could make the barrier lower, higher, in fact, make the barrier zero, make the barrier the opposite sign. He could do all of that here through this particular arrangement. And in a way, what he had discovered was the field effect principle. What was field effect principle? That by applying a potential at an electrode, you could alter the conductivity in the sample here. So this is what he was doing by altering the barrier here, by altering the charges here. Through this particular electrode here, he could alter the charges here. So field effect principle was observed. Something that, this is what they were looking for, a field effect device which could replace a triode, so they could do that. But with a fluid here, with an electrolyte here, with a probe held over here. So this was a kind of arrangement that first showed field effect principle. Well, these results were presented to the group as a whole, and one morning, right? So this is the status of the research. So these results were presented to the group as a whole, and one morning, 1 or 2 days later, Brattain, this is Brattain talking about, Brattain came into my office and suggested a geometrical arrangement to use this effect to make an amplifier. So he came up with why not? It was not an amplifier, it was just a contraption to see field effect. How do you modulate the surface barrier, right? So Brattain suggested a certain arrangement, which you will see, that why not make an amplifier using it? And this was the arrangement. So they got a P-type silicon. They got a P-type silicon with some N-type grown on top of it, N-type layer on top of it. And they had a wire here making a contact to the N-type semiconductor here. And there's an electrolyte here, and there's an electrode here, connection to the electrolyte, right? So let's try and understand what happened. So this is a N-type here, this is a P-type here. And this whole thing is sort of reverse bias. So what is happening is this is taken again from Brattain's Nobel lecture. So he's showing the direction of current. But actually what is happening is the electrons from P-type semiconductor, minority carriers, are flowing into this particular electrode here, into this particular one. Electrons are flowing. So electrons start from here, a large piece of semiconductor here, and electrons will start from here, go into this region here, and this is a thin N-type region. And they would flow from through this thin N-type region into the this wire here, and they would get collected. Right. So remember what is happening. Electrons are starting from here and going into this particular one, while flowing through this thin layer of N-type. And what had they seen earlier? That by applying a voltage to this electrolyte, they could alter the charges in this N-type layer here. So that was the idea, that by applying a voltage here, they could alter the amount of electrons and charges here, and thereby affect this current, which was going from this electrode to that electrode. So it's like a field effect device, but it's turned 90 degrees. It's not a horizontal piece of semiconductor with this. It's like this here with an electrode, gate electrode, if you would like, applied through this here, right? As predicted from this thing here, what they found was they could see the amplification. In this particular device, they use water and different solutions here. They could see amplification, power amplification they could see, but they did not have voltage amplification. But power, whatever was the power here and the power over here and the load was, so they could see power amplification through this particular device here. So an amplifying device had been invented. But note that you have an electrode here and then you have electrolyte here. So the response was very slow, naturally through an electrolyte going through ions migrating from the top or up and all that, the response was very slow. So also they shifted from silicon to germanium. Brattain said, let's try out germanium. Let's see how that works. And they found a much larger amplification with germanium. Okay, much larger amplification with germanium. And in the course of experiments, all right, so let me skip some of these. In the course of experiments, what Brattain noticed was that this electrolyte that they had, they was using glycol borate here, a insulating film was forming under it was oxidizing the germanium surface. And the insulating film was forming here. So he realized that this electrolyte was not directly making a contact to germanium. It was just a means to apply voltage through the dielectric. Right, so he said, why not replace this one here by a metal? Why use a electrolyte at all? If electrolyte, all that it is doing is making a contact to through a insulating film, why use an electrolyte? Why not use a metal here? So that's what they did. So this was the film here. So they said, why not take that particular film and put gold on top of it to apply this particular signal here, and the point contact was supposed to go through the hole. They had a hole in this particular layer of gold, and the point contact was supposed to go through this particular one. And they did experiments, and they got shorting and all that problem between this electrode and that electrode. So what they did was they created this arrangement that, okay, they separated the two out. So here is the point contact, and here is the gold contact made to the N-type semiconductor. And they said, well, let's try it. They had gotten good effect with the electrolyte. So now they said, let's try this out with the with this arrangement here. So note that what is happening in this particular device here. This is a point contact diode here, and what is happening is reverse bias. So what is happening is holes from here are going into this point contact diode here. And what they were expecting is that by applying a voltage here, they could alter this current here. All right. And so they saw this effect that yes, by applying a voltage, they could alter the current flowing between these two pair of terminals. But the effect was just the opposite of what they were seeing earlier. They expected that if you apply, let's say, voltage in one direction, the current would, let's say, decrease. But they found that the current was actually increasing. Just the opposite of what they expected here. So note that what is the reason that the current is flowing? The current is flowing, it's a reverse bias junction. There are holes here, and the holes are flowing into this tungsten. The holes are going from here into this point contact and causing a current. So if the current is increasing when you apply a voltage here, it means that holes are being injected from the other contact holes. So what they realized was that what is happening is that this evaporated gold here in the neighborhood of this particular point was injecting holes. And so this is what, so apart from the holes flowing from the bulk, they had holes which were going like this here, coming from the evaporated gold and then going into this particular contact here, right? These are Brattain and Brattain working together, doing these experiments and coming up with these ideas here. So now that they found that they could increase the current flowing in this circuit by applying a voltage here. So they said, why not enhance this particular effect? How do we enhance? So they figured that this contact and this contact need to be brought very close to each other, because note that holes are being injected here and they have to travel and reach there, right? The holes have, and to avoid recombination and all that, they realized that the 2 points have to be very close to each other. So they came up with this arrangement here. They came up with this arrangement of a wedge kind of a thing. I'll show you a diagram. On a wedge, they had electrodes on the left-hand side and right-hand side, and in between they had a gap. And so they were able to create two contacts, 2 point contacts, very close to each other. Very close to each other. On application of a voltage here, in the first experiment itself, when they applied a voltage here, they got amplification. Okay? In the first attempt, which was successful, contacts were made by evaporating here. So this is a diagram that many of you would have seen, the famous diagram of the first point contact transistor here. Let me read. Using the germanium surface and the gold contacts, the circuit. Now, the way they tested the circuit, they made a demonstration that they were getting amplification by actually through a voice amplification. So the circuit was actually spoken over, and by switching the device in and out, a gain in speech level could be heard and seen on the scope presentation with no noticeable change in quality. So it was a visible demonstration of, look, we are able to do amplification using this new device here. And various people were present that you can see here. The demonstration occurred on the afternoon of 23rd December 1947, which many people take it as the birth of the point contact transistor. Right. So this was the device then that they had invented. Two contacts here, and this is a big piece of semiconductor here. So they called it the base, and the whole action was taking place because this junction was reverse bias. So there was some current flowing in this particular junction. But by applying voltage to this, they could inject holes, which then got collected here, right? So they called it this emitter, and the other one was naturally called the collector. And the whole contraption was sitting on a base on a piece of big piece of semiconductor. So that was called the base here. So that's where the terminologies emitter, collector, and base come into picture here. The transistor, the word transistor was named by Pierce. Bardeen and I, meaning Brattain, wanted a name that would fit in These devices were already there, useful devices, varistor, thermistor, but they didn't have an idea of what to call this particular device. They didn't want to call a solid state replacement for a triode or, a big name, right? So Pierce knew that the point contact device was a dual of a vacuum tube. After some thought, Pierce mentioned the important parameter of a vacuum tube. Vacuum tube, as I said, you can control current through a voltage. And so it had conductance. And this device, what was happening was current injected at a low impedance point was collected at a high impedance point. So current was flowing from a low resistance point to a high resistance point here. And so he described this, the essential property of what they had discovered was transresistance, and he called it transistor. He mentioned transistor, and Brattain said, yes, that's what we are going to call it. So that's how it was, the name was coined. And this is the first paper that came out describing, of course, patents were filed, and Bell Labs kept the whole thing a secret for at least 6 months. During that time, they filed patents and papers and all that were published here. It's the first paper that came out describing what I've just talked about here, the transistor semiconductor triode, right? So the conception is still a triode, right? That's what they're trying to do, replace a triode, so a semiconductor triode here. And what is very interesting, when we talk about the invention of the transistor, we mentioned Shockley, Brattain, and Brattain. Usually the name Shockley comes first, right? And look at the first paper that came out. There's no Shockley here. There's only Brattain and Brattain. I narrated the whole discovery process. Brattain and Brattain are working together. Shockley is not there in the picture at all. The device was invented, and look at the acknowledgement. When Brattain is writing this paper, we wish to acknowledge our debt to William Shockley for initiating and directing the research program that led to the discovery on which development is based here. They're saying, yes, he was a part of it. He was not the, and this point was Brattain, after discovering, inventing the transistor, he left shortly because of problems within the group. He left Bell Labs and went to University of Illinois, Urbana-Champaign, and joined as a professor of electrical and physics both. He joined as a, this thing here. And Brattain's first PhD student was Nick Holoniak, who was one of the inventors of the light emitting diodes. So Nick Holoniak was the first student of Brattain. And I happened to be a PhD student in 1990s, doing my PhD at the University of Illinois, Urbana-Champaign. I took two courses with Nick Holoniak, and he used to often, so Nick Holoniak was a student of Brattain, and in some sense, I was a student of Nick Holoniak. So Nick Holoniak used to talk about the invention of the transistor. And at that point, he would often say, look, Shockley did not invent the transistor. He was a student of Brattain, and he said Shockley did not invent the transistor. He would often talk about transistor. Many times he would reminisce and talk about transistor in the class, and he would say Shockley did not invent the transistor. Who invented the transistor was Brattain and Brattain. And if you go back and see the first transistor, the point contact transistor, Shockley is not involved in this. In this whole process here. Now, there was some confusion as to still, we have emitter and collector. Were these holes that were being injected, were they flowing at the surface or were they flowing in the bulk? And so very interesting thing that occurred was this person called John Shive. What he took was he took this piece of germanium and he polished it in this particular form, in the form of a wedge, right? And he made 1 point contact here and 1 point contact here on the two opposite sides. And he got the same effect that you were getting with this earlier structure. So clearly showing there's no surface here. So he clearly showed that this was a bulk phenomena. This was not a surface phenomenon. So what was happening was the holes were being injected in the emitter, traveling in the bulk, reaching the collector, and then giving rise to that particular phenomenon. If some of you are interested, what was the first transistor like? Okay, so these are the details. It was a block of, I couldn't get the thickness of, what was the thickness of the germanium block. Must have been several hundreds of microns, a very thick crystal here. The doping in the germanium, the first transistor, the doping was N-type, 5 times 10 to the power 4T. That was the doping level. The separation between emitter and collector was around 50 micron. They biased it around, let's say, 100 volts, and they had a load resistance of 40K here. And at the other side, note that is germanium. They were applying, let's say, a forward biasing this particular junction, 0.2 volt, and 0.75 milliamperes would flow through this particular one here. Now, some of you may get surprised. Emitter current is 0.75. Collector current is 2 milliamperes, right? All right, so I'll not go into the details. 0.75, it may bother you. Emitter current is smaller than the collector current. I'll not go because there are many other sources of the current here. They applied a 100 millivolt signal here, and they got 11 volt here, and a power gain of 21 dBs, power gain of around 125. Just some typical numbers that if you're interested here. This was the characteristic that Brattain published of the transistor. Here is talking about the collector voltage. Here is talking about the collector current. So this is sort of, rotated maybe 90 degrees to what we are familiar with. We have collector current here, collector voltage here. So what I did was I took the data from here and replotted it. Okay, here. So that's more familiar. Well, collector voltage here and collector current here. So these are the characteristics of the first transistor that you can see here, right? And it was operated in common base format. So these characteristics are given for different emitter currents here. Okay, and this was the load line. This was where it was biased, and this is what yielded the amplification that I just talked about. The first transistor was commercially produced. It was called a type A because there are many other kinds of transistors that were invented. It was called a type A transistor. You see here. You can see the size of the transistor. All right. Let's come to the Shockley's before we wind it up. Shockley's contribution. The birth. This is Shockley writing in a paper published in 1976 in IEEE Transactions. The birth of point contact transistor was a magnificent Christmas present for the whole group. I shared in rejoicing. But my emotions were somewhat conflicted. My elation with group success was tempered by not being one of the inventors. I experienced some frustration and that my personal effort, started more than 8 years before, had not resulted in significant inventive contribution of my own. In response to this frustration, for the next 5 years, I did my best to put the lab and myself in the lead for transistor patents. So he got very, that he was something wonderful happened, but he was not. He was the leader of the group, right? But he was not part of the discovery process. Some other two people invented the transistor. So he got busy, but he, in fact, of all the people perhaps leaving Brattain, he is the one who understood PN junctions, minority carrier currents, and all that very well here. And very shortly, within 6 months, he published a variety of transistor structures, much better than the point contact transistors. So these were some of his drawings here. You can see a junction. The earlier were point contact transistors. He's using a junction here, and this is more familiar to a schematic that we are familiar with, a N-type and a P-type junction, and in a familiar format here. So this is from his patent in 1948, and this is Shockley describing how the transistor works. So he worked out the theory of PN junctions and transistor and everything, and invented the junction transistor. And it took some years, 2-3 years, for the junction transistor to be actually made. Point contact transistors were forgotten once the junction transistors came into being. Now, so after about 6 months, of course, Bell Labs disclosed the transistor to the world. And as I said, once the news reports came out, this is the most famous photograph of invention of the transistor, with the Shockley sitting in the middle, and Brattain and Brattain were standing by side. And Nick Holoniak used to tell us that both of them were very upset. Both of them were very upset when the press came to take the photograph. He is the one who's sitting down while we are the inventors, right? and the reports that came out, if you read "Local Man Invents New Device," the local man is the Shockley, right? And that's the reason why Nick Holoniak and others would go and say, look, who invented the transistor? A lot of people didn't get it right, right? So this is the famous photograph. But anyway, we realized that they invented the point contact transistor, but the transistor that we have today owes its origin to the work of Shockley. And both of them were, all three of them were honored in this Nobel Prize that was given in 1956 here. So Brattain, if you go and read Brattain's Nobel lecture, so he's, of course, they are giants of the field that we belong to, but he's very humble. He say, what he writes, that we were fortunate enough to be involved at a particularly opportune time to have invented it. Right, this was the right time because silicon, germanium were available in very pure form, and it was a good group of people. There were metallurgists. There were Brattain was there, who was a very good experimentalist. Brattain, who was a theoretical person. The other thing that I want to leave you with is, I mean, if you're wondering what led to the invention of the transistor, so there is, with all these big inventions, there is an element of luck. As Brattain is acknowledging, he's happened to be there at the right place, the right time. There's always an element of luck. But at the same time, if you read, it's interesting to note that the group that was formed, Brattain and Pearson, had considerable experience in the field prior to the war. None of them had worked on semiconductors during the war years. We were able to take advantage of important advances made in the period in connection with the development of silicon and germanium detectors, and at the same time have a fresh look at the problem. Right. So this was very important that they could look at it. They were not biased by all the things that had happened earlier by efforts of other people. They could look at it in a fresh manner. Yeah. This is important, the culture of the group at Bell Labs, which led to the invention of the transistor. Look at the culture of the group. When any novel idea or new experimental results were obtained by any member or part of the group, it was our practice to call the group together for a presentation and discussion. These sessions were inspirational, and it was during such sessions that many of the better suggestions for future work were made. So they had a culture of anybody who did something will bring it to the group and we'll talk about it. And that allowed other people ideas to be shared, and people could work on each other's ideas. Now, there's one other twist to the story of the invention of transistor. It is that there was European inventors of the transistor too. And many people do not know that these two people here, look at their patent. This was filed in August of 1948. Transistor was invented in December of 1947, and the patents and all that came out in June or that. These people filed their patents on also point contact transistors. Okay, and most people do not know Herbert, I don't know how to pronounce, Matare and Henrik Welker. These two people were working at a laboratory in France. There were two German scientists working at a laboratory in France, and they independently came up with the idea of point contact transistor. They patented it also in 1948, but they were not recognized by either the Nobel Prize Committee, while they honored the other three inventors of the transistor. These people were not recognized here. And finally, IEEE Spectrum came out with an article how Europe missed the transistor. So they independently came up with the transistor, but Europe was war torn at that particular point of time. They didn't get much support for further work. In France, the two German scientists returned back to Germany. They did do some further work, but most of the active work took place in US at Bell Labs, Texas Instrument, and other places here. And so we don't, it's unfortunate that these two scientists had also they came up with the idea of a transistor at about the same time. And so I think while we are remembering the transistor, the inventors of the transistor, we should also remember, and there are nice articles, you can find out, go and read about their efforts as well, how what they did and how they invented the transistor. Okay, these are the two people, Herbert Matare and Welker here. All right, so let me stop with, there are many excellent sources. Some of them I've listed, the Nobel lectures by Bardeen, Shockley, and Brattain, this article by Walter Brattain, Shockley's article in IEEE Transactions, and several others that are there. So thank you.